Welcome to the class on EE540 Advanced Electromagnetic Theory and Antennas. I'm Professor Rakesh Singh Chattermem. So we have discussed about the Hertz dipole, and what we have observed was that Hertz dipole cannot be used for any practical application because the radiated power from the Hertz dipole was very less. So in order to improve the power radiated from the antenna, instead of having an infinitesimally small current carrying element, we can extend the size of the antenna, and in the process the power will also increase. So this is the structure of a dipole antenna. So now what you have is, at the center of this dipole antenna we have a source. We are supplying the source to the antenna. So in the upper portion we have a cylindrical conductor of length L, and in lower portion also we have another cylindrical conductor of length L. So now this metal conductor in the upper portion and lower portion are of length L and L, so the length of the dipole antenna is 2L. So now this dipole antenna can be assumed as combination of several Hertz dipole. So you subsection every part of the conductor, small section of length dz, you can assume there is a Hertz dipole. So in the upper portion of the antenna you can have many Hertz dipole, lower portion also you can have many Hertz dipole. That's why we call Hertz dipole as the basic building block for antennas. So now in order to find out the fields radiated from this dipole antenna of finite length, we need to find out what is the current flowing in such kind of antenna. So in order to understand that, let us try to assume a transmission line. So basically you assume a transmission line and you want to find the voltage wave flowing in the transmission line. So at any location Z, the voltage which is flowing in the transmission line can be represented as combination of wave which is propagating along the positive z-axis and another wave which is propagating along the negative z-axis. So the amplitude of the wave for the wave propagating along the positive z-axis is b0 plus, and amplitude of the wave which is propagating along the negative z-axis is b0 minus. So once we have, see, basically what we are considering is transmission line, and there is a load ZL, and this is the characteristic impedance of transmission line. The load ZL is not equal to Z0. In that case, signal which has been incident from this transmission line, after seeing this impedance mismatch at the load, some of them will be reflected back. So now at any point on the transmission line we'll have combination of wave which is propagating along the positive z-axis and wave which is propagating along the negative z-axis. Wave which is propagating along the positive z-axis is the incident wave, and wave which is propagating along the negative z-axis is the reflected wave. So we'll have combination of such kind of two waves. So if you want to find the current along any transmission line at any specific location Z, you need to divide by the characteristic impedance Z0 to the expression you have for the voltage wave. So this expression for the voltage wave, if I divide it by Z0, then I get the current at any location Z. But here you have a negative sign is because from the definition of Z0, Z0 is defined as B0 plus by I0 plus, whereas if you want to define Z0 in terms of the reflected wave is B0 minus by I0 minus with a negative sign. That's why we have a negative sign here. That is because how we define characteristic impedance like that. For the positive traveling wave, Z0 is B0 plus by I0 plus. For the negative traveling wave, Z0 is defined as B0 minus by I0 minus. That's why we have a negative sign here. So now if we take out B0 plus by Z0 common here, then what we have here is, basically when I take out this common, what I have here is B0 minus by B0 plus. So B0 minus by B0 plus is the ratio of the reflected wave divided by the incident wave, which is also called as reflection coefficient. You can also find out reflection coefficient for the load impedance of ZL as ZL minus Z0 by ZL plus Z0, where Z0 is the characteristic impedance of the line. So now if you have an open circuited transmission line, so look at this diagram here. We have a conductor here. This conductor at this point is open circuited, no? So at this end this conductor is open circuited. So let's say some current is flowing in this conductor. At this point current will see an open circuit, so we can model this as open circuited transmission line. So in that case, in the open circuited case, ZL will become infinite. So ZL minus Z0 by ZL plus Z0 will become 1. So in that case, reflection coefficient will become 1. So now this gamma here will become 1 when you have an open circuited transmission line. So the expression you have for IZ will be V0 plus by Z0 exponential minus J beta Z minus exponential plus J beta Z. So this you can express in terms of sine function. So it becomes minus 2j V0 plus by Z0 sine beta Z. So this is expression for the current flowing in a open circuited transmission line. But here you need to make some simple changes here. It's because at the end when Z is equal to L, so we are supplying some AC source here. At the end when Z is equal to L, we should have a zero current because this is terminated here. Signal or current which was flowing through the conductor won't be able to go anywhere here, so it sees a termination here. So here what should be the current at this open terminal? It should be 0. So now this expression of the current density is not taking care of that condition. At the two ends the current should be equal to 0, so we can make a simple modification in the expression for current density or for the current at any specific location Z as minus 2j B0 plus by Z0 sine beta L minus modulus of Z. With this modification, whenever Z becomes plus L or minus L, current will become 0. So current should be equal to 0 at the two ends of the conductor, and that is satisfied by this expression you have for the current along the dipole antenna. And you can even simplify this expression by putting I0 is equal to minus 2j B0 plus by Z0. Then in that case IZ will become I0 sine of beta L minus modulus of Z. You can plot the current distribution for different length of the dipoles. Let's say if I want to, so what we are going to do is we are going to plot this current distribution, but we are going to do it intuitively, looking at the current which is flowing in a transmission line. Can I plot the current distribution of dipoles of different length? So usually in a transmission line the current would have form like this. The current distribution would be like this. You will have maxima, negative maxima, then positive maxima, then at the end when you have open circuit, current will become 0. So current distribution for a transmission line will be something like this: 0 here, then again 0, you have maxima here, you have again negative maxima here. So this is usually the current distribution along a transmission line. But let's say if we are considering case of a dipole which is very small length, so if the length of the dipole is less than lambda by 8, so the total length of the dipole was 2L. If 2L is less than lambda by 8, what we can do is we just cut this transmission line at lambda by 8. So if we cut this transmission line at lambda by 8, what is the current distribution? At the open end it is 0, and at this point where we are cutting the transmission line we have the maximum current distribution. So now you cut this portion of the transmission line and bend it upward and downward. So this portion you bend it upward, this portion you bend it downward. What should be current distribution? At the end you have 0, and at the point where you're cutting the transmission line it has a maximum current. So this is almost like a straight line when this length is very small. In that case this would be like this. So at the end you have 0, at the center you have maximum. Similarly you cut this and draw the current distribution. At the end you have 0, you have maximum here. So this is the current distribution of a dipole whose length is less than lambda by 8. So the current distribution we have drawn is done intuitively. You can even find it out from the current distribution we have derived in the previous slide, but we like to do it intuitively. So So this is a transmission line with open circuit. This is the current wave inside the transmission line. So now let us consider the case when the antenna or the dipole is of length lambda by 2, or in that case L will become lambda by 4. So L will become lambda by 4 in that case. So you cut this antenna here, you cut this transmission line here, then bend it upward. Cut this transmission line, bend it downward. So now this length is lambda by 4, this length is lambda by 4. So at the end you have zero current. At this point where you have lambda by 4, you have the maximum current. So this looks like a current distribution of this form here. So lambda by 2 dipole will have current distribution like this, maximum at the center and minimum at the two ends. Similarly, you can also draw current distribution of an antenna of length dipole of length lambda dipole. So lambda dipole means this will be lambda by 2, half wavelength, this will be half wavelength. So you cut this transmission line at half wavelength. What is the distribution? You have minima here, you have maxima here. So at the center you have a minima, at the two ends also you have a minima. So the current distribution for the lambda dipole would be like this. You can even keep on doing it. Let's say you want to find the current distribution of a 3 lambda by 2 dipole. So what is half of 3 lambda by 2? 3 lambda by 4. So this portion will be 3 lambda by 4, this portion will be 3 lambda by 4. So you cut the transmission line at 3 lambda by 4. At 3 lambda by 4 you cut it. What you have at the end is this. Then you have minima, then negative minima. So this is what it looks like. So at the end you have 0, then positive maxima, then again 0 at lambda by 2, then again you have a negative minima here. So similarly for the lower portion, you cut it here, you bend it downwards. So the current distribution would be negative minima, then you have a 0 here, the positive maxima here, you have a 0 here. So you can easily draw the current distribution from this process and this heuristic process of drawing the current distribution. And that way, just looking at the antenna structure, you will be able to say what is the current distribution of the antenna without doing any mathematical derivation. So the question is, we have the current distribution, and how do we find the fields from the current distribution? So now you already know that for a Hertz dipole, what is the far field, electric field and magnetic field. So now for a Hertz dipole, what is the far field? Electric field is like this. Far field, magnetic field, you can find out from the electric field by dividing by eta naught. Electric field will be along theta direction and magnetic field will be along phi direction. So now let us look at the diagram of the dipole antenna of finite length. So in the diagram at the center you have a AC source and it's supplying current to the this upper arm of the dipole antenna and lower arm of the dipole antenna. So you can subsection this upper arm of the dipole antenna into small sections of length dz, small section of length dz, and some current is flowing in that. So that is an infinitesimal current, small current carrying element. That is basically what you call Hertz dipole. So you know what is the electric field produced by this small current carrying element in the far field of the antenna. So if you want to find the total field radiated from this dipole antenna, you have to integrate it from minus L to plus L. So first thing is that in the far field of the antenna, what happens to the, see, basically this is the source. Now we are considering this Hertz dipole here, the source here. Observation point is P in the far field of the antenna. So distance between the source and observation is R1, and distance between the origin and the observation point is R. So now when you are in very far away distance from the source, these two lines are parallel. So that is the far field approximation. R1 and R will be parallel, and R1 minus this distance will give you R. So this R, position vector of the observation point, should be R1. R1 should be slightly lesser than this R. This R is distance between the origin and the observation point. This R1 is distance between the source and the observation point, this R1 will be slightly lesser than this R. How much that will be lesser? That will be this region here. So now you know that this dz is located at a distance z from the origin. So, and this angle is theta. In that case, what is this length? This length is z cos theta. So if I want to find R1, R1 will be R minus z cos theta. So R1 will be R minus z cos theta. For the expression for the amplitude of the electric field and magnetic field, you don't need to make this approximation. 1 by R1 will be approximately 1 by R. But for the phase term, this phase term here, you cannot neglect this minus z cos theta from the R. So R1 will be R minus z cos theta. In that case, you replace the phase term exponential. What was that? Exponential minus j beta R1. So you can write this as exponential minus j beta R exponential plus j beta z cos theta. So the phase term changes like this, but amplitude term you can just replace R1 by R. So as I already told you, this dipole length was of 2L. So if I want to find the total radiated field from this dipole, I need to integrate it from minus L to plus L of this dE theta, which is the electric field produced by a dz element of the dipole of finite length. You have to integrate it. So when you do the integration, look at this term here, which are the term dependent on dz. Which are the term dependent. See, we are doing integration of dE theta with respect to dz. Z is going from minus L to plus L. So in this expression, you just need to worry about the integration which are dependent on the z. So you have exponential j beta z cos theta. You also have Iz. Current flowing in the dipole was I0 sine beta L minus modulus of z. So this term and this term are dependent on the z variable. So when I do integration, all other terms I can take it outside. So the derivation for this electric field, total electric field due to the upper arm and lower arm of the dipole antenna, is done in the book I have written for electromagnetic field theory. Derivation is little bit lengthy, so I have already explained in the book. So if you are interested, you can refer to the book. So the final expression would be of the form J60 I naught exponential minus j beta R by R, and this term f theta, which is the function which will decide the radiation pattern of the antenna. So f theta turns out to be cosine of beta L cos theta minus cos beta L by sin theta. So this term will give you the radiation pattern of the antenna. So you can draw the radiation pattern of the antenna from that function f theta. So you will have E plane and H plane of the radiation pattern. You can see that this function f is only a function of theta, is independent of phi. In that case, the H plane of the H plane radiation pattern of the antenna will be a constant for every angle of theta, so it becomes a circle. How about the E plane radiation? So this E plane radiation, what you can observe, is dependent on the L, which is the half the length of the dipole. So depending on L, capital L, you will have different radiation pattern. You can plot it. Let us consider when 2L, total length of the dipole antenna 2L is lambda by 2, 2 lambda and 4 lambda. You can plug in the value of L in this expression and you can plot it in MATLAB. This is the radiation pattern we are getting. When the length of the dipole is lambda by 2, the radiation pattern looks like 8. E plane radiation pattern. H plane radiation pattern, as I already told you, looks like a circle because E theta was not having any variation with respect to phi. E theta only has variation with respect to theta, and it's given by the capital F theta function. So depending on the length, this variation of electric field with respect to theta is going to change. So for particular case, when you have half wavelength dipole, which is the most widely used dipole antenna, what you have is maximum radiation along theta is equal to pi by 2 and theta is equal to 3 pi by 2, zero radiation in 0 and pi. And you can observe that when the length of the total length of the dipole antenna is 2 lambda, you have 4 major lobes and they are directed along 60 degree, 120 degree and 300 and 240 degree. So you have 4 major lobes when you have a dipole of length 2 lambda. if you have a dipole of length 4 lambda, you have 8 major lobes, 1 2 3 4, 1 2 3 4. So this pattern you can plot from the function f theta, which has been given. This I have done using the MATLAB. You can also do it. So some points to be noted for the dipole antenna of finite length. First thing is the input impedance of the dipole. So if you want to find the input impedance of the dipole, you should find out the impedance at z is equal to 0, that is the center of the dipole. So if you want to find input impedance of dipole, that should be input voltage divided by the input current. So now at z is equal to 0, what was the current? Current will be I naught sine beta L, and this is the input voltage you are giving to the dipole antenna. So one point to be observed is that for the dipole length of 2L, when L is a odd multiples of lambda by 2, or 2L is a odd multiple of lambda by 2, L is a odd multiple of lambda by 4, or 2L is a odd multiple of lambda by 2, in that case you can see that sine beta L is equal to 1. So this term becomes 1. In that case, Zin will become simply B in by I naught. So you can find out the input impedance of antenna if you know I naught and B in. And another case is when you have 2L is a multiple of even multiple of lambda by 2, or L is a even multiple of lambda by 4. In that case, sine beta L turns out to be 0. In that case, input impedance is equal to infinity. So now, if input impedance of the antenna is infinite, you won't be able to do proper matching of the antenna with any kind of fit line you give to the antenna. So for any input source, the transmission line which connects to the antenna will be of 50 ohm, but input impedance of antenna is infinite, so you will have a maximum reflection at the input point of the antenna, so there won't be proper radiation. So this even multiple of lambda by 2 for the length of the dipole of 2L is not used for practical application because of the problem in the impedance matching. So we usually take 2L total length of the dipole antenna odd multiple of lambda by 2 because impedance matching is easier for that. And as you already know that as the length of the dipole becomes more and more, the total radiated power increases. Size of the antenna increases, total radiated power also automatically increases. And electric field has only theta component, and so it's linearly polarized along the theta direction. We can also find out the nulls in the radiation pattern. So null of the radiation pattern when your capital F theta is equal to 0. So that means there is no radiation along that direction. You can find out. So what was capital F theta? Capital F theta was cosine of beta L cos theta. We are trying to find out theta null, so theta becomes theta null minus cos beta L divided by sine theta null is equal to 0. So null will occur when cos of theta null is equal to plus 1 plus minus m lambda by pi. So when m is equal to 0, what happens? Cos theta null is equal to plus minus 1. In that case, theta null is either 0 or pi. So we have a null radiation along 0 and pi for the dipole antenna of finite length. So but then you see that here when theta null is 0 or pi, sine of theta null will also become 0 or pi, so it becomes indeterminate. So numerator is also 0, denominator is also 0, so this function becomes indeterminate when theta null is equal to 0 or pi. In that case, you can find out the limit by taking theta is equal to 0. So we take a limit theta is equal to 0 or pi. What we have here is capital F theta is cos of beta L cos theta minus cos of beta L by sine theta. So now you can have an infinite series expansion for cos of beta L cos theta is basically 1 minus beta L cos theta whole square by 2 factorial plus beta L cos theta to the power 4 by 4 factorial minus what is cos of beta L? Cos of beta L is 1 minus beta L square by 2 factorial plus beta L to the power 4 by 4 factorial. And so on. We'll have higher order terms here. I've neglected it. So in that case, you can simplify it, combine the term, this term, and this term, this term, and this term. What you get is limit theta tends to 0 pi. What we have here is beta L square by beta L square sine square theta by 2 factorial minus beta L to the power 4 1 minus cos of 4 cos to the power 4 divided by 4 factorial, and don't forget we have 1 by sine theta here also in the denominator. So when you divide by sine theta to this expression, finally what you have is limit theta tends to 0 to pi beta L square sine theta by 2 factorial minus beta L to the power 4 sine theta 1 plus cos square theta by 4 factorial, and so on. What you see is that whenever theta tends to 0 or pi, this function is becoming 0, this function is also becoming 0. It means when limit theta tends to 0 or pi, the function capital F theta is giving 0. So even if this denominator itself is also giving 0, but the limit overall of this function f theta is 0, so we have a null of the radiation for cos theta null is equal to plus minus 1 plus minus m lambda by pi. So sometimes it's very difficult to find the null radiation pattern of the antenna. What you usually do is you find out the maximum radiation. So let's say if you want to find out the maximum radiation, how do you do it? You have the expression for the radiation pattern f of theta, you differentiate it with respect to theta and equate it to 0. Find the value of theta for that. That value of theta will give you theta max, which is the direction of maximum radiation. Then after that you find the first two nulls. So basically finding this theta max direction may be difficult because sometimes the expression for f theta is very difficult, very complicated. So f theta expression, if it is very complicated, differentiating it with respect to theta and equating to 0 may be very difficult. So what you do is instead of doing that, you can just find out the first two nulls and assume that center of the first two nulls is usually theta max. So this is another way of finding theta max. The proper and mathematical way of finding the theta max is you differentiate f theta with respect to theta and equate it to 0. What is the value of theta for that? You get theta max. Or simpler way is you first find the first two nulls of the radiation pattern of the antenna and center of that will be theta max. So what is the radiation resistance of a dipole antenna? So you can find out radiation resistance as 2 total power radiated divided by I naught square. So you know what is total radiated power is basically you integrate the radiation intensity with respect to d omega. D omega is sine theta d theta d phi, because you know that d omega is dA by r square. dA for this case is r square sine theta d theta d phi. So you divide it by r square. In that case, d omega will be sine theta d theta d phi. This is the radiation intensity. You integrate over sine theta d theta d phi over theta is equal to 0 to pi, phi is equal to 0 to theta is equal to 0 to pi, and phi is equal to 0 to 2 pi. You get the total radiated power. Once you have the total radiated power, you can find out the radiation resistance by multiplying with 2 and dividing by I naught square. So if you want to find out the radiation intensity, you can find it out from the Poynting vector by multiplying with r square. So you have the expression for the electric field E theta. So if you want to find H phi will be E theta by eta. So you have the expression for the Poynting vector. Once you have the expression for electric field and magnetic field, you can find the expression for the Poynting vector. You multiply it by r square. This is the expression you are getting. So final expression for u theta phi for any dipole antenna of finite length is 30 by pi I naught square cosine square pi by 2 cos theta divided by sine square theta. So if you want to find the total radiated power, it will be 30 by pi I naught square integration of this term here from theta going from 0 to pi. So this integration is not easy. Sometimes you have to make numerical approximation to find out this integration, to find out the total radiated power of a dipole for any arbitrary length. So there is another antenna which we use frequently. Is like, for example, if you have seen the so you know you can listen to FM in your FM radio in your car, no? So let's say while you are driving your car, you can also listen to music from FM radio. So those kind of radio signals are actually picked up from the antenna you fix on the rooftop of your car, no? So such kind of antenna which are fixed on the rooftop of your car or any other place, let's say you have a conductor is there, you fix another one antenna, which people usually call as monopole antenna. You have a dipole antenna, you cut it into half and you fix the upper arm of your dipole antenna on a conducting plane. Those kind of antennas are called monopole antenna. So this is what we are showing here. You have a ground plane which is made up of metal. You actually fix a monopole antenna which is the half of the dipole antenna. So now from your image theory, whenever you have a current flowing in this monopole antenna in this direction, you can have another image of that by see basically in the image theory what you do, you replace the ground plane by you remove the ground plane and the effect of the boundary condition of this ground plane of the original problem can be satisfied by replacing a image current density. So that image current density, this is a vertical case, so vertically directed current density here, you will also have another vertically directed current density here. So this is the image of this monopole antenna. So this looks like dipole in free space. And so the properties of monopole antenna can be easily interpreted from the dipole antenna, because after putting the image of the monopole antenna, this overall structure looks like a dipole antenna. So since your monopole antenna has only the upper arm of the dipole antenna, the total radiated power of the monopole antenna will be half of that of the total radiated power of the dipole antenna, because the size has been reduced by half. No? Monopole antenna length is L, whereas dipole antenna length is 2L. So the total radiated power will be half that of the dipole antenna. So if the total radiated power is half that of the dipole antenna, monopole antenna will have a radiation resistance which is half that of the dipole antenna. Another thing is that directivity of the monopole antenna will be twice that of the dipole antenna. That is because, how do you find the directivity? You find out directivity as 4 pi times radiation intensity in that particular direction given by theta and phi divided by the total radiated power. So the total radiated power for the monopole antenna is reduced by half, because we are just using the upper arm of the dipole antenna. In that case, we have a half in the denominator, so directivity will become twice. You can also analyze one simple antenna which is called loop antenna. So in the olden days where you have CRT based TV, TV, we don't in our days we don't have a TV which has a flat screen. We usually have a TV with a CRT. So in that case, people usually use antenna which are called loop antennas. So these loop antennas can be in circular shape, triangular or square or elliptical shape. We'll consider loop antennas in the circular shape. So there are two kinds of loop antenna. One is electrically small loop antenna, another is electrically large loop antenna. The electrically small loop antennas will have circumference which is less than 0.1 times lambda. Lambda is the operating wavelength of the antenna. For the electrically large antenna, the circumference will be greater than or equal to lambda. This electrically small loop antennas like Hertz dipole doesn't have proper radiation, it doesn't have any practical use. But electrically large loop antennas, I have already told you, it was used in TV in the olden days. Let us try to analyze this electrically large loop antenna. This structure of an electrically large loop antenna, it's in the form of a circle. You have two coordinate system, one for the source which is the prime coordinates, one for the observation which is the unprime coordinate. So now you can find out the magnetic vector potential for this loop antenna. It is already given in the book I have written for electromagnetic field theory, you can refer to it. So the expression for A phi would be of the form mu I naught A exponential minus j beta r. What is A? A is the radius of this loop, divided by 4 pi r pi j j1 beta a sin theta minus j1 minus beta a sin theta. What is beta? Beta is the wave number for free space. A is the radius of the loop. These are Bessel function. J1 is the Bessel function of first order. You know that there is an infinite series expression for the Bessel function. We have discussed it in one of the classes. So this is the infinite series expansion for the Bessel function of order n. So if you put this argument minus z, what happens? This term will become minus 1 to the power n j n z. When n is 1, what happens? J1 minus beta h sin theta should be equal to minus J1 beta h sin theta. So in that case, this minus and minus will become plus. In that case, A phi will have an expression like this. Once you have the A phi magnetic vector potential, I can find the electric field easily. So this process of finding the electric field from the magnetic field, magnetic vector potential, you have a minus j omega A here. So we have, what do you have? We have minus del of electric potential minus dou A by dou T. Dou A by dou T for time harmonic fields becomes j omega A. And here minus del of electric potential, you can find it from the Lorentz-Gauss condition, applying Lorentz-Gauss condition here. So electric field you can find out from this simple expression you have here. So when you find out the electric field, and we can even simplify this for far field approximation. When you have far field approximation, your electric field E theta will be simply minus j omega A theta, and ER will be minus j omega AR, E phi will be minus j omega A phi. So in the far field of the antenna, your electric field and magnetic field has a simple relation. E theta is minus j omega A theta, ER is minus j omega AR, E phi is minus j omega A phi. You can derive this. So if you are interested, you can explore. So now what do you have? We just have A phi. All other terms are 0. A theta and AR is 0. So E phi will be minus j omega A phi. We have already derived A phi in the previous class. So electric field will have only phi component, and this is the expression for the electric field. One point to be noted is that electric field is varying as 1 by r, and it is transversal to the radial direction of the wave propagation. So if electric field has only phi component, magnetic field will have only theta component. You know that ratio of electric field and magnetic field is equal to eta. So if I want to find H phi will be minus E phi by eta here. So eta is 377 ohm for free space. So you know the expression for E phi, you can plug it in here, you can find the magnetic field now, H theta. You have a negative sign. Why do we have a negative sign is because we know that pointing vector is radially outward. If I don't put a negative sign here, when I do cross product of electric field and magnetic field, I will have a radial vector, pointing vector which is radially inward, which is not possible. Pointing vector should be radially outward physically, because wave is propagating away from the source. So if I put a negative sign only, then I will have a pointing vector along that direction, positive radial direction. So in the following slides, we'll look at the radiation pattern of a loop antenna, and it can be observed that as the size of the loop antenna, radius of the loop antenna A keeps on increasing, that means size of the loop antenna keeps on increasing, the radiated power becomes larger. This will be very clear from the next diagram you have here. So this diagram here shows the radiation pattern of the loop antenna. What was the expression? Electric field E phi is dependent on the theta, so it's independent of phi. So in that case, in the H plane, the electric field will have a constant value for any value of phi, so you will have a circle. But for the E plane, this is dependence of the electric field with respect to theta. So you have J1 beta A sin theta here. You can plot it easily in MATLAB using a command for the Bessel's function. So when you plot it, what you see is the E plane of the radiation pattern of the antenna. What do you have here? These dotted lines are for radius is equal to 0.1 lambda. This is very small antenna. When radius become 0.2 lambda, this is the dashed line here. When the radius become 0.3 lambda, this is a solid line here. You can see that total radiated field along this direction keeps on increasing when we increase the radius of the loop dipole antenna, loop antenna. So increase the radius, increase the size of the antenna, total radiated field is higher and higher. That means total radiated power will also become higher and higher. That is logical. And one major simplification is when you consider a electrically small loop antenna. When you have a electrically small loop antenna, in that case beta A will be less than 1 by 3. If beta A is less than 1 by 3, we have a approximation for J1 Bessel functions of order 1. J1 beta A sin theta can be approximated like this: half beta A sin theta minus 1 by 16 beta A sin theta cube plus, and so on, higher order terms. So when beta A is a very small number which is much lesser than lambda 1 by 3, the higher order terms will become smaller and smaller. You can neglect it. You can just consider this first term here. The approximation of J1 beta A sin theta will be simply half beta A sin theta when this argument beta A is a small number, and when A is very small, beta A will be very small. So in that case we can approximate J1 beta A sin theta as half beta A sin theta. So in that case E phi will become, electric field has phi component, E phi expression will become like this, and magnetic field has phi theta component, it will be minus this expression you have here. So if you compare this expression for electric field and magnetic field with that of the Hertz dipole, they are very similar, except that for the dipole polarization was along theta direction, but for the loop antenna polarization is along the phi direction. Otherwise the expression is very similar. So you can even assume small loop antenna of electrically small length as a Hertz dipole and find out the radiation pattern. But point to be noted is that polarization of the antenna for the dipole antenna and small loop antenna is different. Dipole antenna, Hertz dipole antenna, is polarized along theta direction, whereas small loop antenna of electrically small length is polarized along the phi direction. Thank you. That's all for this class.